Okay. Yeah, okay. So let's start. And so in this fifth lecture, I will continue what I started today with the fourth lecture on the description of quantum simulators based on Rydberg atoms and on interaction between Rydberg atoms. So I show you again here the two timelines I use for guiding my lecture. So yesterday I focused more strongly on the lower part, the technical aspect of realizing optical tweezers and the various steps which were important for that. Then I had a presentation of the properties of the Rydberg atoms and why are they interesting for quantum simulation. And basically, the interest is the long-range interaction, so that even if atoms are micrometer or 10 micrometer away in different optical tweezers, they still have strong interaction. And today I will go rather along the upper line, where you have the kind of physics which was demonstrated and investigated with this kind of quantum simulator. And I will first focus on a theoretical proposal by looking at Zoller in 2001, when they introduced the dipole blockade phenomena as a tool to efficiently perform quantum gate. And it was kind of the triggering of this long story. So I switched to part 3 of this, which is indeed description of experiment performed in the van der Waals regime using simulation, performing simulation of the Ising Hamiltonian, which is also the same interaction which is used in the dipole blockade proposal by Lukin and Zoller. So this dipole blockade was introduced in 2 papers, which are listed there. And basically, you can see the principle of dipole blockade depicted on this drawing. So you have a 2-level system. G is the ground state, R is a Rydberg state. You assume you have some Rabi frequency, either 1 or 2 photon Rabi coupling between these 2 states. And the point is that if you have a pair of atoms, once a first atom is excited from a pair of atoms in G, then due to dipole-dipole interaction, the energy of the pair with 2 atoms in the Rydberg level is shifted. Here it is shifted upward, and the shift increases as 1 over R6. So if you go to short enough distance, the laser, which is resonant to the one Rydberg excitation state, is not anymore resonant for exciting 2 Rydberg level. And there is a blockade. You excite 1, but never more in the region of space where atoms are closer than what is called here the Rydberg blockade radius, which is indeed determined by the ratio between the line width of your laser line, of the excitation line, and the magnitude of the van der Waals shift. So it means that if you have a collection of atoms in optical tweezer, but this also works with atom in atomic vapor, then once a Rydberg atom appears in the system as a result of excitation, it is forbidden to have a second one there, which build correlations in the system, and that's a way to build many body correlations in the distance, for example, between the Rydberg atoms. So then here is the status, the evolution of the experimental observation of this dipole blockade phenomena, the inhibition of excitation of pair states if the atoms are close to each other. Indeed, the first paper about that was pretty older than Lukin-Zoller proposal. It was a paper published by Jean-Michel Brune and Serge Haroche in 1981, when they observed, and this is a figure from the paper, that at that time it was no tweezer, it was just atomic beam experiment with atoms completely disordered. But they remarked that when you try to excite a high density of Rydberg atom, you do not manage to do it due to this dipole blockade phenomena. So at that time, the system was very disordered, and it looks like a messy thing to go to high density of atom without tweezer, and we forgot about this, and for a long time we went not in this direction, but after looking proposals, then there was a series of experiments demonstrating this effect. So this first family of experiments were not performed with tweezers, but in a cold of with a cloud of ultra-cold atoms. And then, after this work on disordered atomic sample, the two first two-atom experiments were performed in 2009 in parallel in the team of Mark Safman and the team of Antoine Brouwer. So I will now describe these two first observation of the dipole blockade in two-atom synoptical tweezer. I would like to mention the principle of Lukin-Zoller gate because it's very simple. And so you can see that you consider two atoms, and that's the principle of a quantum computer that Lukin is presently developed. The qubit states encoding the quantum information are states of the two hyperfine sublevel of the ground state of rubidium, which means that they are non-degenerate in energy, and that when you send a laser which couples to the Rydberg level with a two-photon transition, the laser is tuned so that it can excite the atom in state 1, but not in state 0, because it's non-resonant. And the interest of this scheme is that you can have very long lifetime for quantum superposition state of this qubit state, because hyperfine coherence, if you choose properly magnetic and sensitive states, are very long, like seconds or even longer than that. So with this qubit encoding, the principle of the gate, the two-atom gate, is like this. You apply to both atoms, to one atom, you apply pi pulses with these blue pulses at the Rydberg frequency omega-1, and on the second atom, you apply a 2 pi pulse on the same transition, but you have to address the atoms individually. And then what occurs as a result of this interaction, you can easily check. If both atoms are in 0, they are never resonant, they don't see the laser, so nothing happens. So 0, 0 remains 0, 0. In all other three cases, you have a minus sign showing up as a result of interaction, but the state is always the same on both sides. So how does it work? For example, let's take the second line here. If this is in 0 and the other in 1, 0 does nothing, so it is as if these two blue pulses were not there. But the pulse for the second atom will perform a 2 pi rotation. And 2 pi rotation of a two-level system provide a pi phase shift. So a minus sign here shows up. If, on the other hand, you start with not the second, but the first atom in state 1, so let's assume 0, then the first pulse performs pi pulse, second pulse does nothing to 0, and third pulse finishes 2 pi pulse, indeed, for the first atom, and leads to this minus sign. And same kind of thing occurs for the last state. And if you look at this truth table, it corresponds to the unitary evolution of a controlled phase gate. So maybe usually you are reading the controlled phase gate with a minus sign here and plus signs on the three other states, but within a global phase, it's exactly the same. And that's the kind of phase gates which are combined in the now very complicated experiment and the very developed operation Lukin performed in this group in the direction of quantum computing, and which allowed him to combining this gate with motion of the atom in the ground state. They managed to perform advanced quantum information manipulation, like encoding a logical qubit in 48 physical qubits and implementing some kind of error correction. So that's the idea for the gates. Let's go now to the first two-atom realization, and I will describe the experiment performed in the group of Antoine Brouwer. So van der Waals interaction is here, and I here just specify the states which are used in the experiments. They perform first the experiment with the 58D free half and 58D free half, two atoms in the Rydberg level is the 58D free half. So if you just consider the van der Waals interaction for atoms separated by 10 micrometer, it's a little bit too weak for having a strong dipole blockade. And then at that time, they play a trick, which is important because we also play it, and many different people want to use this trick to enhance the interaction by using a so-called Forster resonance. So what does it mean, a Forster resonance? It means that if you look in the detailed structure of the Rydberg level, you may have coincidence between the energy of two pair states involving different Rydberg levels. And here, the coincidence they use is the degeneracy of energy between 58D, two atoms in the same level, with a pair, if you pick the 60p level and the 56F 5 half is the G quantum number of this, then in a very small electric field, you can put them exactly at resonance. And if you look at this state, you have a dipole matrix element between the D and the P state of the first atom. You have a dipole matrix element between D and F state. So there is a first order coupling due to dipole Hamiltonian, which means that you expect a splitting of this bare energy level as a result of interaction. And then the interaction becomes stronger as compared to the van der Waals interaction because it's first order, and it varies as 1 over R3. So in the experimental conditions, this allowed one to double the strength of the interaction at 10 micrometer, and they perform even the experiment at shorter distance, like 3.6 micrometer between the atoms, so that the energy shift of level is 70 megahertz, and that the dipole blockade is stronger. So here is the scheme of the experiment for achieving this. So in this experiment, they arrange the trapping beam so that it produces two traps at the focal plane of a spherical length. You see around the lens a set of 4 electrodes, and you can imagine that there is a second lens with another set of 4 electrodes, allowing one to control the electric field in 3 dimensions. For D levels, it's important to be with a homogeneous field in the experiment, so there is a preliminary step where people cancel the stray electric field using all these sets of electrodes, and then they perform fine-tuning of the Forster resonance by adding some bias field along the quantization axis, which is set in this experiment by, I think, a magnetic field. So laser excitation is a 2-photon transition. At that time, it was not the blue laser first and the infrared second. It was first infrared laser 795 and then 474 nanometer laser, but this scheme is not so advantageous. The lifetime of 5P here is shorter than that of the 6P level, which is involved in the other inverted excitation when you invert the role of the blue and the red. But historically, this was this kind of excitation. It produced 2-photon Rabi oscillation. And then the experimental timing is like there. So they first load single atom in the optical tweezers. They eventually rearrange them to have exactly 1 atom per tweezer. Indeed, no, this was before rearrangement. So they just post-select randomly the experiment where the first image tells that there was exactly 2 atoms. So the trap is switched off at some time so that when you send the laser pulse exciting the Rydberg level, you don't have to deal with inhomogeneous light shift induced by the traps. And then after a delay of like 500 nanoseconds, you switch on the trap and you compare what you detect on 2 images, whether the atom which was present off on the first image does disappear or not. It's the signal you have as a signature of the excitation of the Rydberg level. So in the first experiment, they put the atom very far away from each other at a distance of 18 micrometer, so that the interaction is made negligible, and they make 3 experiments. In the first experiment, they only prepare atom A, and you see the Rabi oscillation of an atom, a single Rydberg atom, submitted to the laser pulse. Then they do the same with only atom B, and you get the green line, which is very similar within noise with respect to the green one. And then they perform the experiment with both atoms present. And you see that basically when both atoms are present, you still have Rabi oscillations. They are a little bit less contrasted, and indeed they are just less contrasted because what you expect for independent atom is that the signal is a product of the red and the green data here. And the blue line, the blue dots correspond to the product of the single atom signal. And you see that the 2 atom signal is just within noise the same as the product of individual atom signal, which means that the atom behave independently in this first experiment. Then they reduce the distance between the atom and perform basically the same measurement. So green and red data are the same, are taken in similar condition as there. So noise difference. So they redid the measurement with this shorter distance. And then the product of independent probability is now this blue line. And the signal detected when they prepare a pair of atoms is again the black line and the black data. And you see that excitation is strongly suppressed. And that was indeed the first observation of dipole blockade with a pair of atoms in their team. So you see the blockade is not yet perfect. No, it's much better, but it was the first experiment, and they understood well through experimental imperfection what was there with the actual data. So that's the point for this. And then let us go not to interaction of just pairs of atoms, but let us enter the field of the many-body physics that can be investigated by this system. And I will introduce the Ising Hamiltonian, which is the first one which was used in this kind of experiment, which corresponds to the regime where you have the van der Waals interaction between atoms and where the qubit states or the effective spin states are encoded in the ground state of the atom for one of the level. So here for rubidium, it's the F equal 2 hyperfine level, and with optical pumping, you select one M sublevel, let's say the maximum value of M equal 2. Then Rydberg level is varied depending on the experiment. It's either NS or ND Rydberg level, which are the 2 kinds of level accessible with a 2-photon laser excitation from a S level. And here is depicted the general form of the Hamiltonian that you can simulate and whose parameters can be adjusted by varying various experimental parameters. So indeed, I listed the parameter you can vary in the Hamiltonian here. And so in this expression, you have a first parameter showing up, which is delta, the detuning between the 2-photon transition and the sum of the energy carried by the laser exciting the atom. So that's the 2-photon detuning of the lasers, and it acts like an effective magnetic field longitudinal along the quantization axis that is defining these spin states. Then, if you go to the second term, it is proportional to the Rabi frequency, the 2-photon Rabi frequency on the atomic transition, and it is proportional to sigma x. Then, and indeed, you know that when you are at resonance, Rabi oscillation performs rotation along, let's say, the y-axis, which means that Rabi oscillation is generated by the sigma x rotation operator. So this generates the so-called transverse field of the Ising model. Then the interaction term is characterized by the parameter Jz, which has a form of a C6 coefficient divided by the 6th power of the distance between the atoms. And then Ising corresponds to a product of sigma z of the two spin. And here I just consider the Hamiltonian written in kind of linear chain with just next neighbor interaction, but this generalizes easily to 4 dimensions. So usually for Ising, the 1/R6 variation of the interaction ensures that most of the physics is the interaction with the first next neighbor, which is not the case later when we'll consider the exchange Hamiltonian, whose scaling with distance is 1/R3, and then when the next neighbor is responsible for some of the part of the physics. Typical values of this parameter in the range of 0 to like 10 or 50 megahertz for the tuning and Rabi frequency, and the coupling can be varied in a broad range from 1 to 100 megahertz, when the distance typically between atoms is varied between 10 micrometer to like a few micrometer. In looking experiment, the distance is of the order of 3 micrometer between the atoms. So that's the Hamiltonian that we want to run. And now I describe one of the first experiments where this Hamiltonian was run in a case of a chain of 51 atoms. Indeed, in parallel, this Hamiltonian was also run in the team of Antoine Breuers, who performed a 30-atom experiment on a ring. But here I will focus on the work performed in Harvard first. So what do they do? Indeed, they have a linear chain of atoms which are prepared by the rearrangement technique involving some acousto-optic deflector with a lot of different frequencies sent to the acousto-optic deflector, and then atoms compressed and reordered. So let's assume that they have prepared this chain with exactly 1 atom per tweezer, and they send a focused pair of excitation laser here along the axis of the tweezer to perform the excitation to the Rydberg level, which was chosen to be the 70S Rydberg level. And then they observed, indeed, a very nice feature of the dipole blockade phenomena by performing Rabi oscillations in this system for different number of atoms in some small clusters they can prepare in the chain. So they can have up to 51 atoms, and they can prepare the atoms in tweezers which are very far away with respect to each other, or prepare the atom so that interactions are completely negligible, and then they can prepare a pair of atoms where the interaction is strong within a pair but negligible with the next pair, and then go to 3 atoms and eventually even more. And what you expect, indeed, is that when you have a single atom of, okay, you observe the single atom Rabi oscillations that you observe with any 2-level system submitted to the laser. With pairs of atoms, its distance is smaller than the dipole blockade radius I already introduced, and they perform this experiment with a bit less than 3 micrometer between the atoms. Then an interesting many-body phenomena occurs, leading to the generation of an entangled state of the atom, which is deeply related to the dipole blockade phenomena. And what occurs, you see that the Rabi oscillation goes faster when you have more atoms interacting with the same laser, which means that there is some collective aspect in the interaction between the atoms. So there is dipole blockade, so at this distance you can ignore the probability to excite a pair of atoms with a very good approximation. But if you consider that you have n atoms in the cluster, then indeed the laser produces a collective coupling of the n atom to this W state, which is a quantum superposition of all atoms except one and then you vary the position of the one excited atom in this collection of n, and you sum over all the states. And then you normalize with this factor 1 over square root of n. And you see that the Rabi oscillation for n atom is a coherent evolution between these two states. It's a two-level system. All other combinations you can build orthogonal to that are not coupled to the ground state here with all the atom in the lower state. And if you calculate the Rabi frequency characteristic of the coupling between these, you have n term in the matrix elements. And as so it's multiplied by n, and you have this normalization factor. In the end, the effective Rabi frequency for n atom is omega square root of n. So they observe this square root of n enhancements with n equal 2 and 3. So the frequency they measured are exactly in the right ratio. And indeed, that's you can see that's a way to prepare some entanglement in the system by using dipole blockade for two atoms. This is an EPR pair. If I encode spin up and spin up in G and R, then it's the equivalent of up down plus down up. And then the entanglement of this kind of states was fully characterized in this kind of experiment. So then they, with the same system, they made a little bit, yes? Yeah? Yes, so here the dipole, the distance between the atom is small enough so that all the three atoms are within the blockade sphere and not just a pair. And that makes the transition with the next situation where the idea is to play with the parameter so that the next atom is eventually blocked, but the next one is not. And that's what they play in this second experiment performed with the same system. So here is again the Ising Hamiltonian, and they start to play with preparing some different ground states of the system by starting with a trivial state, which is all atoms initially in the ground state. And then by adiabatic variation of the parameters, you can transform this trivial state into a more interesting one. And here is presented on this kind of phase diagram, where the horizontal axis is the ratio between the tuning and Rabi frequency, so ratio between longitudinal and transverse magnetic field. You see that when you start with a very large negative detuning, you can check that the ground state corresponds to all the atoms in the lower state of the transition, which is all the atoms in G, what you prepare naturally in the tweezer experiment. But if you vary adiabatically this parameter, you enter in regions where, depending on the range of interaction, so on the size of the dipole blockade radius, the ground state becomes, after adiabatic passage, this kind of ordered states with here in the Z2, so-called Z2 state, one atom over 2 is excited in the Rydberg level. And that corresponds to the regime where you set the dipole radius just in between the parameter A, which is the distance between two atoms, and 2A, which is the distance to the next debut. So in this parameter range, if you go the adiabatic transfer, here is the profile of the detuning as a function of time, and the blue line is the profile of the Rabi frequency as a function of time, which is basically essentially a square profile for the Rabi frequency. So everything is the subtlety of variation of the detuning in order to efficiently prepare this Z2 order state. Then if you vary the interaction strength, you can eventually, by increasing the blockade radius, prepare a state where only one atom over 3 is excited in the Rydberg levels, or even one atom over 4. So let us focus on the Z2 states that I prepared adiabatically in the experiment. So here is the evolution as a function of time of a collection of 13 atoms submitted all to the same laser pulse. The laser pulse is hitting all the atoms in the same way. And as a function of time, so time scale is like 10 microseconds, you see that initially the fact that you have all red here means that all the atoms are in the ground state, and then one atom over two is promoted to the Rydberg level in the adiabatic transfer, which is here. And if you make a cut of this data with the vertical lines, you see the population of the various levels. So it's not perfect Z2 state, but it's a pretty good approximation. So then a very nice thing is that once they prepare this, they discover an unexpected, interesting many-body phenomena. So after preparation of these two states by the adiabatic transfer, they make abrupt quench of the system by switching off the detuning and the Rydberg frequency. And then the system starts to evolve. It's not eigenstate of the Hamiltonian in the presence of interaction. And what they see is oscillation between two Z2 states, one where the end atom of the chain are excited, and the other one here at that time where the less excited atoms are at the end of the chain, and the excitation now sits in between the initial state. And the amazing thing is that these oscillations looks like a long-lived oscillation without the expected damping. So it was something robust, which is a many-body phenomena related to the existence of what is called quantum scars in the spectrum of this many-body system. So quantum scars were introduced in a chaotic quantum system and were a way to identify robust, long-lived regularities in the system. And here they were observed, so I don't want to make a detailed description of what occurs there, but indeed this experiment realizes the so-called PXP model of the many-body physics. It's nothing else than another word for saying this Hamiltonian in this dipole blockade regime. And then, by looking in details, by analyzing the experiment in detail, it was shown, especially in this paper, that the phenomena was related to this quantum scar phenomena. So let's go one step further with even more atoms. We were in the range in 1917 of a few tenths of atom, up to 50 atoms. And then I will switch to experiment where basically 200 atoms were involved in order to demonstrate preparation of anti-ferromagnetic many-body states in two-dimensional array. Up to now, I have considered one-dimensional arrays, and we enter at that time, 2020, so not so far away from us, in the physics of the many-body physics of 2D system. So let's focus on this experiment. So what is this famous antiferromagnetic order? Basically, it consists in generalizing what I explained in one day, the fact that when you adiabatically vary the parameter of the system, you can go to a state when 1/2 atom is excited. So in two-dimensional, when you start with your tweezer, with all your tweezer with unit filling, after some adiabatic variation of the Hamiltonian, you end up with half of the atoms in the upspin state, the other half in the down state. And indeed, you see that every time you have an upspin within experimental imperfection, the next neighbor, the closest neighbor, is in the down state. So that's the definition of this antiferromagnetic state. And indeed, the two experiments by Boers and Lukin were demonstrating this kind of effect in a very similar way in parallel. On one side, 196 atoms. On the second side, 256 atoms, which does not make a very big difference between with respect to physics. So let's say a little bit more about the states which can be prepared to have to get an idea of the degree of control they have in the experiment. And so on the left side, you have the experiment performed by Antoine Brouès. And indeed, here is the detailed way they choose to adiabatically vary the parameter to go into the region of space where the system is antiferromagnetic, which is the 2D equivalent of the Z2 phase diagram, phase appearing in the 1D diagram previously. So they vary the parameter in that way. The red line is the detuning, the blue line is the RB frequency. You see that time scale is typically a few microseconds. Here it was 6 microseconds. Case of looking is 3 microseconds, a little bit different profile, but in the end, they prepared very comparable antiferromagnetic state. And what is amazing is that how efficient is the method to prepare only one state, and indeed they prepare either one or another one, so there are two perfectly antiferromagnetic states in the setup. You can see that here you have excite one sublattice of this, and the other states correspond to exciting the complementary sublattice. And there's two slaves within negligible boundary condition effects are both equivalent and antiferromagnetic. And then on this graph is a representation of the population of a given state. So here, these two peaks corresponds to the population of the two antiferromagnetic states in the huge size of the global Hilbert states. If you have like 200 spin, the number of states you have in the Hilbert state is already 210 to the 19. And it's amazing that they really, in the distribution of the populated states, that they measure by repeating the experiment a lot of time and looking at the image. So the image which are favored, strongly favored with respect to the background are the two ideally expected antiferromagnetic states. So if you look at the probabilities, these peaks emerge, but the sum of the population in all the other states is indeed dominant, but it corresponds to very often to one or two defects in the lattice. And so if you put the number, the probability you have in two peaks in the raw data corresponds to only 2% of the realization, but it's already a tour de force. And indeed, the main imperfection here is the measurement imperfection. At that time, the fidelity of measurement, detection error of the atom was in the range of 1 to 3%, so they measured it carefully. And if you can correct these 2% for detection error, the state which is effectively prepared in the experiments is nearly up to 30% of the case, the right one, which is already impressive for a 2,000 atom system. So Lukin experiment had similar performance, but instead of running an 8 by 8 lattice, they run it with a 12 by 12 lattice, and you see that exponentials are very fast because the number of states goes to 2 to the 19, to 10 to the 19, to 10 to the 43. So it's a huge number already. And in a similar analysis, you have in the raw data 0.03% of perfect antiferromagnetic. And if you correct for about 1% detection error, you have 0.1% of ideal state. So here, when you go from this experiment to that one, you see that it's efficient. And of course, this number is larger, but this is much smaller. So in the end, performance of both experiments are comparable. And if you reduce the number of atoms in the Lukin experiment, you would have similar numbers there. So that's really a very pregnant, very prominent demonstration of the ability to manipulate now hundreds of atoms and to prepare with very high efficiency the ground state of this Ising Hamiltonian. Of course, this does not demonstrate new physics because this ground state is well known, so it's kind of benchmark of the present experimental ability. So one step further in benchmarking this is to look not only at the individual state of the atom, but to measure, by analyzing the image, the correlations between the atom, to have a measurement of the length over which they can observe antiferromagnetic correlation. So from the data, they calculate this number, where n is the number of Rydberg atoms at a given site, so it's either 0 or 1. So you calculate the average of the product of n minus the product of averages, and then you plot it in a 2-dimension as a function of these two indexes, which represent the distance between the 2 points for which you look at correlation. So you measure this by averaging over the whole lattice, and you get, in both experiments, some checkerboard shape correlation function pattern, which are clearly characteristic of anti-ferromagnetic order. So in the case of the experiment performed in Institut d'Optique, indeed, they made a very precise comparison between the experiment as it is with a theoretical model based on a matrix product states calculation, including the known imperfection of the experiment. And you see that the upper half of the graph is the experiment, the lower part of the graph is the theory, and it's very, very similar, which means that MPS is good to capture the physics of the system, but also that all imperfections included in the model are realistic enough to describe properly the system. And if you compare the correlation length you get from the experiment with the one you get from the theory, theory predicts 7A, where A is the lattice spacing, and the measured correlation is about 5.5 times A. So a little bit reduced, but it's already a very nice agreement. So then, to make you feel the limit of the numerical simulation based on MPS, you can say, okay, MPS is there, we don't need the simulator. So a little bit increase in the size of the simulator may put the system out of reach of the MPS technique. So here they go from an experiment with 10 by 10 lattice, 100 atoms, with 14 by 14, around 200 atoms. And then you are unable to predict what you measure within a realistic calculation time using MPS. The system is already too big, it's 2-dimension, and the theory fails to describe this kind of simple ground state system. So it's kind of first demonstration of a quantum advantage. You already, with this 200 atom array, enter a field where the theory have limited abilities to describe the system. Then similar results were obtained in the group of Michel Brune with an array of a size which is a little bit larger, with a little bit reduced imperfection, so that the correlation length was more than 10 times the distance between the lattice side. So that's really a point where a toolbox was really ready to perform a lot of things with the Ising Hamiltonian. Maybe I just mention what was done here by mentioning some paper I will not have time to discuss, but which were performed in the line of exploiting this Hamiltonian with many atoms. So a very first experiment related to the simulation of topological matter was performed in the group of Antoine Brouwers, where with a chain of 14 atoms arranged in the zigzag geometry, they managed to simulate the so-called one-dimensional SSH Hamiltonian, which is kind of the simple toy model, simplest toy model to have a body system demonstrating topological features. So there was a very nice demonstration of this with a 14 atom chain. And then later, Lukin performed a first experiment trying to characterize the properties of a spin liquid, which is also another topological state. And indeed, there is still a strong activity around that because it's not so easy to characterize spin liquids. The observable you have to measure is not so clear, and there are discussions between theoreticians. And I know that presently Michel Brune group and Antoine Bresbrook try to have a more clear demonstration of the properties of this kind of state of matter, which is predicted by theory, but which was never observed. So now let's go to the second kind of Hamiltonian that you can simulate. After having described the Ising Hamiltonian, we'll consider the exchange Hamiltonian, which leads also to very interesting many-body physics. So what is the exchange Hamiltonian? I already shown that slide in the first lecture. The dipole-dipole interaction in the regime where the two atoms are in the same state correspond to the van der Waals regime are already discussed this morning. And now we switch to the situation where the two atomic levels involved are both Rydberg level instead of having one ground state and one Rydberg. And then the K for describing interaction is what is called the exchange. So you see it's based on the fact that when you have two Rydberg levels, one S and one P, which are dipole-dipole coupled, you have degeneracy automatically for free between two pair states where either the first or the second atom is an S state and vice versa for the P states. And as a result of dipole-dipole coupling, if you prepare this system, you get in the in the energy spectrum a splitting of energy level with new eigenstates, which are positive and negative superposition of these two states. So this is very simple feature of two-level systems. This is well known. And then the strength of the interaction is characterized by the C3 coefficients, which involve the matrix elements of the transition there, divided by the third power of the distance. So you see that this is always a resonant interaction, and if you prepare one of the states, it's not a steady state of the system, and the evolution will be the so-called flip-flop evolution, where the energy, the energy stored in one of the level is given in one of the atom will be transferred to the other atom and back as a function of time. So then I have a little bit more local diagram of what happened as a function of time, focusing of the use of this flip-flop Hamiltonian. And then the story started in 2015, where first experiment involving 3 atoms were performed, and I will focus on this experiment. So in this experiment, they manipulate up to 3 atoms. Indeed, I will just describe the symbol part of the experiment, which is the demonstration of the operation of exchange Hamiltonian with a pair of atoms. So I consider that only 2 of the tweezers are loaded, and the third one is used for another purpose in the paper. So in the experiment, they choose to use not a S level, but a D level, 62D and 53 P level. And indeed, there is a kind of flexibility to choose the level. If you choose a principal quantum number larger by 1, 2, 3 or less, it's not critical for this experiment. So they choose it so that the exchange frequency in the range that was comfortable for the experiment. So then you expect a splitting between these two, and they prepare in the experiment first the 2 atoms, one in 62D, the second in the 63P, by using this excitation scheme. So both atoms are trapped. As usual, as soon as they start Rydberg excitation, trap is switched off for the full time of the simulation. And so during that time, first laser pulse is addressing the first atom. So here they address the atom individually with the laser pulse, and they do this by indeed, they send the same excitation laser of both atoms, but one of the atoms, the upper one, so the two lines correspond to the two atoms. The upper one is light shifted using a focus beam, which hits the first atom, but not the second, which is generated in a similar way as the trapping lasers. So first laser pulse, atom 1 is blocked, atom 2 is excited to the upper level 62D, which is spin up in our spin terminology. Then there is a microwave pulse transferring up level to down level, which is the 63P, and this does nothing to the other atom, which is still in the ground state. So here at this point, they prepare G down, and then they send a second optical pulse to the atoms without having blockade applied to the first atom, to atom 1, which means that the first atom, which was not excited, now becomes excited, but the P level here is not resonant with this laser, so it's not affected. And so this experiment demonstrates for the first time an important feature of quantum simulator. You can address optically the atom and have different Hamiltonian applied to different atoms by using the local light shift technique. So using this technique, they prepare the up-down state. Both atoms are in the Rydberg level, but one is in the D and the other in the P, which is not eigenstate of the system. So you start to have Rabi oscillation between these two levels as a result of the dipole-dipole coupling. So then they wait for some time, so that this red arrow, during which exchange interaction occurs. And at some point, they stop basically the interaction by sending again a blue laser pulse, which put back the D part of the population to the ground state, and they look at fluorescence. So in this experiment, they detect only one of the Rydberg level by putting it back in the ground state and looking at fluorescence. Of course, the P level is non-resonant with the laser, so remains in the Rydberg, and indeed it is expelled from the tweezer when we switch on the light of the tweezer again here. So that's the result of the experiment, where you have, as a function of time, the population, the excitation of both atoms. So the blue line is corresponds to the population of up-down state, which is initially prepared, and the red line corresponds to the population of down-up state, which is the state to which the system oscillates. So you have nice exchange interaction with some finite contrast, which can be, again, understood by the imperfection of the experiment at that time. Of course, this is, every time I try to present you the first demonstration of the effect, of course, this was much improved for doing something out of that, and the fidelity, the present fidelity of the exchange oscillation, which can be observed, is much higher than that. And then they perform the experiment for several distance between the atom, and they check the 1/R3 scaling of the exchange Hamiltonian. So the toolbox is now also ready for performing a quantum simulation with the XY Hamiltonian. So there was very different steps here. So there is a list of the paper. Indeed, at the end of the lecture, there is I have to edit, but I have a list of all the references, and it was also the case for the first lecture. You had at the end of the slide a list of all references related to what I presented. So I will focus now on one of the experiments recently performed with the XY Hamiltonian in 2023. And indeed, this experiment was performed in a very similar, more sophisticated experiment was performed a little bit later, which is also very interesting, but that I will not have time to discuss in detail. So here, again, I will not discuss the details, but tell you that indeed what was done for preparing antiferromagnetic state with the Ising Hamiltonian was also performed in similar way by adiabatically varying the parameter in order to prepare the so-called anti-ferromagnetic state of the XY Hamiltonian. So you could think, okay, it's just another variety of antiferromagnetic state, but it's kind of equivalent to Ising. Indeed, it's more tricky than Ising, because Ising, you consider spin which are antiparallel with respect to some quantization axis, and the thing is simple. Every spin, one is up, the next is down, and so on. Here you have to be aware that in the way they prepare the thing, they start basically with all spin pointing in the horizontal direction. Okay, so they start with some states, vary adiabatically the parameter, but the many body states, antiferromagnetic here in 2 dimensions, with the spin in the horizontal plane is much more tricky. Because in the horizontal plane, which is perpendicular to quantization axis, there is no privileged direction, X or Y. So even if I represented, or they represented here, the antiferromagnetic states like you have every next neighbor antiparallel to the next, then the same picture applies for the other direction. Let's say this is Y, but X is Y. And the ground state is a superposition of all these. So it's much more fuzzy state, and the physics then in the end is different. So they prepared this state, they characterized it. I have no time to go into the details, but finally they managed to measure the dispersion relation of the excitation of the system, which is a very nice demonstration of the kind of things you can do with this atom in tweezer to characterize the many-body state in the case of the XY Hamiltonian. Okay, so that's what I wanted to say about the present status of quantum simulation performed with the Rydberg atom in low angular momentum Rydberg level. And in the last part of the talk, I will go closer to what we do in OLAB and to where we are in OLAB by discussing the perspective of quantum simulation using circular Rydberg atom. And first, I'll show you where this is located in the timeline. Indeed, we started this circular Rydberg atom stuff by writing a theoretical proposal in 2018. And then we start to build an experiment to implement this proposed quantum simulator based on circular Rydberg atoms. And then we reached several steps. We demonstrated the trapping of the circular atom in the tweezer, which is an important feature of this system, because all the experiments I discussed here up to now were performed by switching off the trapping laser during Rydberg excitation. So Rydberg atoms were just free-flying, which is a dangerous situation for the simulator, because when they are free-flying, they just move randomly according to the residual temperature of the atom in the tweezer, which can be low, but if you wait long enough means like 10 microseconds, the atom can start to have moved from the initial position, and then the distance between the atom is not anymore under control, and you see that it's a limitation for long time scale quantum simulation. So for circular atom to use them for a long time, we implemented trapping, then we characterize the dipole-dipole interaction, and we demonstrated a way to measure the circular atom without destroying them, which is not the case of the measurement performed up to now, where basically Rydberg levels are detected by putting them back in ground state, which is destructive for the information carried with the Rydberg atom. And so we are here now, and the many-body physics should come soon, I hope, with the circular atoms. So why is it interesting to switch with circular atom, which are, I already discussed this, more complicated to excite as compared to the low angular momentum Rydberg atoms. So let's look at two of the experiments I have, which were already performed with low angular momentum Rydberg level. This one you already have seen is this experiment performed in the group of Michel Brune, and here is a more recent experiment performed in the group of Antoine Brouwer when they characterize the many-body states of the XY antiferromagnet. If you look at time scale in this experiment, here is like 3 microseconds, here is 10 microseconds, which is close to the limit of this experiment. Not only due to the residual atomic motion, which comes a little bit later, but there is even a stronger limitation related to the radiative lifetime of the Rydberg levels. So if you consider low angular momentum Rydberg levels considered typically in this experiment, SPD levels, then lifetime is in the range of 100 microseconds if principal quantum number is between 50 and 80. This varies by less than a factor of 2 in this range. And half of the spontaneous emission is due to optical transition, not directly to the ground state, but eventually in 2 or 3 steps. And the other half is a microwave transition between the low angular momentum Rydberg level and neighboring Rydberg level. And this is enhanced by the presence of blackbody radiation for this experiment, which are performed at room temperature. Blackbody radiation dominates this microwave transition, and half of the lifetime is related to that. Which means that if you cool down the setup in order to get rid of blackbody radiation, you win a little bit of lifetime, but you don't win more than a factor 2. If you switch to circular atoms, it's going another way, which is much more advantageous. So the point is that if you consider a circular state, let's say 52 circular level, which is your favorite, then there is only one decay channel. You have no optical decay channel for the circular level, because the dipole selection rule tells you that the only dipole transition from here to have efficient spontaneous emission is a microwave channel to the next circular level. Delta L equal 1 selection rule have to apply. So which means that instead of having all that stuff that you cannot avoid, you only have the microwave, and then if you cool down your blackbody radiation not to 0 Kelvin, but realistically to 4 Kelvin, you expect a lifetime on this transition of 10 milliseconds, which means that you win 2 orders of magnitude over that. And how is this number related to this time? Indeed, you can think that this is okay, it's much longer than that. We don't care so much. But if you are simulating a system with like 200 or 100 atoms, this lifetime means that after 10 microseconds, you already lose 10% of the atoms. So it's already a huge number of defects in the system. And your lattice, which was perfect in the initial state, becomes with 10% of holes or defects after that time scale. So you see that if you increase by 200 of magnitude the factor of merit of that, you can either go much further away in time, like 100 times longer, or you can go to much higher number of atoms without having defects after this kind of time scale. So that's the interest that motivated Ed to build a Rydberg atom quantum simulator based on circular atoms. Of course, for taking advantage of this long lifetime, you need to implement trapping of the circular Rydberg atom. So let's go into this business, and here I like to show people involved in the group in this kind of work, and I will focus on the work performed by the rubidium team, which is led by Clément Serrin, who is permanent researcher in our group, and you can see here the PhD students involved in this project. So circular level, here is a more complete diagram of the landscape, the energy landscape of the Rydberg level when you apply some electric field. So the problem is to deal with the degeneracy of a heterogenic multiplicity, which contains like 2,500 levels for typically such kind of principal quantum number. So there are many levels, and it's interesting because it gives eventually a lot of flexibility for the kind of Hamiltonian you can simulate, which will not be limited to spin 1/2. But let's start with a simple situation of spin 1/2. You have to isolate a pair of levels in this forest or in 2 forests if you want to couple 2 multiplicity with different quantum number. So the important point here is that there is a strong regularity in the structure of the energy levels. This is a so-called Stark diagram plotted for rubidium, which looks like this diamond shape. And the good point is that you have, in presence of electric field, the magnetic quantum number is still a good quantum number. So here is this horizontal axis is the magnetic quantum number. So here are sitting the low angular momentum Rydberg level, which are used in the other experiments, which are easily laser accessible, but which have the lifetime limitation I just discussed. So if you go at the end of the tip, the last level with the maximum value of m is, of course, the circular level. And in the experiment, we typically presently use 54C and 52C and 54 C level for encoding the qubit state or the spin state for simulating some Hamiltonian. And then the lifetime is limited by decade channel to 51C, for example, for 52C. Unfortunately, presently, the experiment is not at cryogenic temperature. It's room temperature experiment, which means that this decay is enhanced, and unfortunately, lifetime of circular level at room temperature is similar to the one of low angular momentum Rydberg level, but it's long enough to demonstrate some interesting, important first step for building the simulator. So the first step is to implement trapping, which is not implemented for low angular momentum. And trapping of circular state, or more generally of Rydberg state, is more tricky than trapping ground state atom. Ground state atom, it's easy. It's just enough to have a Gaussian beam to focus it, and that's it. If your optic is good enough, you have a nice trap. Indeed, Rydberg levels are a low field seeker. They are expelled from high intensity region due to the fact that the main force operated on the electron is a so-called ponderomotive force experienced by a free electron. Indeed, in the Rydberg level, the electron is not very strongly bounded. It slowly moves on a circular orbit for the circular level. And indeed, with respect to interaction with the laser, it is as if the electron was free. And the ponderomotive force, which is represented here, expels the electrons from the laser and expels the Rydberg atom from the laser. So in order to trap the atoms, you have to put light all around it. And we use what we call bottle beam, which can be easily generated using SLM, but indeed which are much more sensitive to aberration as compared to Gaussian beam. And so we had to implement some sophisticated aberration correction technique in order to have them good. But the good thing is that they are a three-dimensional trap. So you see the ring, of course, is performing the radial confinement. And on the axis of the beam, here is the cut about around the plane like this. You see that the light intensity increases very fast on the axis. There are some regions where the potential is a little bit lower at some angle, but still you can have a significant trapping potential, which is a three-dimensional trapping potential using the bottle beam. And then in the experiment, it's again more tricky than with a usual Rydberg level. We have to combine two kinds of array for trapping the atom generated by two different SLM, either Gaussian tweezers for the ground state atoms that we switch to bottle beam tweezer as far as we excite the atom in the Rydberg levels. So here is a scheme of the setup we use to manipulate the circular atom. So UHV chamber presently is at room temperature. We have two sets of SLM in order to prepare either the Gaussian or the bottle beam tweezer, and we use acousto-optic modulator to switch on and off the two structure very fast. Changing the programmation of the SLM is slow, and it's too slow to recapture the atom in the bottle beam. We have acousto-optic deflector in order to rearrange the atom and start with ideal lattices. And what is original with respect to other experiments is what is inside the box here. I have just represented two aspherical lenses used to focus the beam and then to take the light out of the setup. But inside we have this complex structure, which is made, basically, it's a cube of insulator, which is sapphire. Sapphire is a good thermal conductor when it will be bring at low temperature in a cryostat. And it holds many electrodes to control the electric field in 3 dimensions around the atom to apply the radio frequency field I already mentioned, which is needed for circularizing the atom. Around that, there are coils to apply some magnetic field. And indeed, the important direction is the horizontal direction, where you have the trapping laser and the aspherical lenses are held by these small lens holders. So we set up this. We started just as everybody to prepare single atom in the Gaussian tweezer, look at images. So that is one of the first images we get. It's a bit noisy, now it's better, but you see that even like this, you have a very good discrimination between the fluorescence peak corresponding to either 0 or 1 atom. We are in the collisional blockade regime, and we can start the business with the Rydberg atoms, the circular Rydberg atom. So the first thing we did is to demonstrate the trapping. So for demonstrating the trapping, we started with an array of atoms with 1 atom per site in the ground state. We performed circularization in several steps. First, laser excitation from 5s to 52D, two-photon transition, as everybody. Then a microwave transition to the 54F. Then a radio frequency transfers with sigma plus polarized radio frequency photons. And we transfer most of the population in the 52 circular state. Then we switch on the trap and wait for some time. And to demonstrate trapping, we just reverse the circularization process to selectively put back in the ground state only the atoms remaining trapped in the 52 circular level. And we look at the recapture rate of the atom as a function of duration of trapping. And then lifetime measurement result is here. The red dots corresponds to the variation of number of recaptured atoms, which is the signature of the circular atom, as a function of time. So you see that it decays very fast. If you have no trap, this decay time is related to the temperature of the atom, which is like 15 microkelvin in the experiment, which means that after a few 10 microseconds, the circular atoms are moving due to finite temperature and are not anymore at the right place when we switch on the tweezer again after the circularization. So if you switch on the trap, you see that it's much more efficient to recapture the atoms, and that corresponds to the blue data. And you can see that recapture is better. It's not perfect. So why? Indeed, this signal is dominated by the finite lifetime of the circular atoms. We recapture selectively only 52 circular levels. And indeed, what occurs during trapping, atoms interact with the blackbody photon around there. And if they are transferred to neighboring Rydberg levels, they are not captured anymore. So the lifetime here of about 125 microseconds quantitatively corresponds to what we expect from the contribution of blackbody radiation. So then we switch to this scale, which is the same red and blue data in log scale. And we plot in addition the green data, which are corrected from blackbody radiation effect. And you see that basically for 1 millisecond, this time scale is 1 millisecond, you lose no atoms. So all the losses are just a blackbody induced transfer between Rydberg levels. And then after this 1 millisecond, we observe a residual decay rate of 5 milliseconds, with probably a very big error bar, because when you are at 1 millisecond or afterwards, you are more than 10 times the lifetime of individual atom, which means that the statistics is very, very poor, and you may have some background, some side effects. So most probably trapping time is even larger than that, and this number is already in the range of the expected lifetime of the circular atoms. So trapping is good. Now let's switch to interactions. And indeed, for going to interaction, we prepare the atom by pair. And indeed, we prepare, so in this lattice structure with 3 pairs. The pairs are far away, are separated enough so that they do not interact between each other. So we put several pairs just to increase the signal to noise. But the physics is that of an individual pair. And in the experiment, we prepare both atoms in the 52 circular level, and we make microwave spectroscopy on the 1 photon transition from 52 to 51 circular level. So in the absence of interaction, indeed, the microwave pulse will eventually promote one circular level in 51C, and the second microwave photon will populate the 51C, 51C level. If I switch on the interaction, and I consider here only the first order dipole-dipole interaction, because van der Waals is much weaker, then what occurs is that this intermediate state, which is degenerate, whether you put 51 circular on the first or the second atom, again, the same story, dipole-dipole interaction splits this level in two with the strength characteristic of the interaction strength. So when I scan the frequency of the microwave inducing 52 to 51 transition, I expected a shifted peak and some kind of blockade effect with respect to that transition. So that's what we did in the experiment. And here you can see, as a function of the microwave frequency, the spectrum of the 52 to 51 microwave line. And indeed, you observe two peaks, which does not correspond to the splitting between these two. Indeed, this peak is coupled, but this has no matrix element with the microwave due to this minus sign. So this we cannot see, but we can still see that because sometimes one atom is missing. This experiment was performed without rearrangement, which means that you can directly go from here to here, and you still have some excitation, which is due to single atom. Or you can also have a non-resonant two-photon microwave transition from here to here, which leads to a second peak. And indeed, there is one peak which does not move when we vary the distance of the atom. So there's kind of reference peak, which is the frequency of the transition without interaction. And the second peak corresponds to this red level, which is shifted and which is coupled with the microwave. So you see the splitting as a function of distance. We can fit the data and plot here again in log scale the variation of the shift as a function of distance, and we get the expected 1 over R3 variation of that. So typically, the dipole-dipole interaction is 3 gigahertz at 1 micrometer, which means that it's 3 megahertz at 10 micrometer. So the clock of the simulator is in the range of megahertz. So we varied the angle between the quantization axis and the interatomic distance, and we observed the anisotropy of the dipole-dipole interaction, but I don't want to say more about that. And then I switch to the more original part of our work, which is the implementation of an optical way to detect the circular atom, which a priori is not easy because circular atoms have no optical transition. So it's not easy just to send a photon and then send a laser and then detect optically that there is a circular atom. Of course, we would like to have this optical detection, not only for the ground state atom, but the circular atom. So here is the method we used up to now. Essentially, we decircularize the atom and we perform fluorescence. And the point is that it's a destructive method of detection. And for performing quantum simulation and also quantum computation, it's interesting not to destroy the qubit, to have non-destructive readout, so that you can eventually implement feedback of the system for performing error correction, or so that you can measure the system at different time to access time correlation in the system. And what I will present you to finish my talk is a method of non-destructive detection of the circular atoms that will be called the target qubit here by using an ancilla atom that will play a role of a probe, which is not promoted to circular state, but to low angular momentum state, which will fill the presence of the circular one and provide an optical signal by looking at the probe fluorescence, which is the signature of the presence of the circular state. So how does it work? Again, the same story. We use a Forster resonance between a circular to circular transition and a low angular momentum to low angular momentum Rydberg level. And here we choose a coincidence in the frequency between the 54 circular to 53 circular line and the 45P to 45S transition. So we choose that, but indeed there are a lot, and you are not completely constrained to this. If you change the principal quantum number, you look at the Rydberg spectrum, and it's rich enough so that you find a pair of levels which is close to resonance, and then you fine-tune it with the electric field. So let's consider that. As usual, Foster resonance leads to a splitting between these two degenerate states, which is the effect we use for detecting the atom by the kind, again, of dipole blockade effect. So if one atom is in the 54 circular level, you expect that excitation of 45s ancilla atom by the properly tuned laser is blocked due to this energy splitting. On the other hand, if the circular atom is prepared in a state which does not belong to this multiplicity, and that's why we consider the 52 circular state as the other spin state, 52 circular level will not lead to this blockade. And then, if you look at the state of the probe, you may discriminate whether you have prepared the circular atom in 52 or 54 circular state. And then, the truth table of this interaction is that if the target is in 54 states, it leads to blockade and the probe remains in 5s, whereas if you have not a 54c, which means it will correspond in the experiment to 52t, then the probe will disappear, will be promoted in the Rydberg level and lost when you switch on the Gaussian trap again. So here is the signal we get and the way we run the experiment. So we start with both atoms in the ground state, and then we perform circularization of only one of the atoms. So here again, we need to use the local addressability that is already used in the other experiment. So we prevent the probe to be promoted to the circular level by applying a light shift. So we have a focused tweezer, which is controlled by the acousto-optic deflector, that light shifts the probe atom and prevents it to be excited by the laser and then to be promoted to the circular level. So at that step, we have one circular atom, one probe atom, and we put the atom close to the circular so that the dipole blockade will be complete during the quantum non-demolition measurement. So the distance is 7 micrometers. So then we perform the rest of the experiment. Eventually, we prepare the 54 circular state by a 2-photon microwave transition. The probe in 5s does not see this excitation. Then we try to excite the probe, and depending whether the circular is prepared in 52C or 54, the probe will be excited or not. And then we perform fluorescence imaging of the probe. Indeed, we also detect the circular atom by decircularizing it and measure it destructively so that we can compare destructive and non-destructive measurement. And here is the spectrum of the probe excitation, depending whether when you decircularize, you detect either 52C or 54C. So that's a conditional signal you obtain by post-selection over the result of destructive detection of the circular atom. And you see that if the circular state is prepared in 52C, the spectrum of the probe corresponds to the black data, and you have a nice narrow excitation of the probe. The probe goes to 54S, which means that the fluorescence of the probe disappears, and basically we do not recapture the probe anymore. On the other hand, once you prepare 54 circular level, dipole blockade is nearly perfect, and you see that as a result of the splitting between the coupled energy level of the system, which is like 40 megahertz, so it's a big effect. Indeed, if you set your probe laser at resonance, the probe excitation is completely inhibited by the presence of this atom. And indeed, you have a very nice contrast between these two measurement posts, which means that you can perform quantum dot demolition measurement of the presence of 54C with a fidelity of about 96% that we understand when we put all the imperfection of the experiment, and which have a significant contribution of the finite lifetime of the Rydberg level during the operation of the measurement. Of course, this will be better at low temperature. So then we perform Rabi oscillation of the system on the 2-photon 52 to 54C experiment. I don't want to say too much details about this, but indeed this Rabi oscillation is a signature of the quantum non-demolition character of the measurement. Here we perform the Rabi oscillation after preparing by a pi over 2 pulse a coherent superposition of 52 and 54. And then this coherent superposition, we measure with a pulse on the ancilla, and depending on the measurement result of the ancilla, we observe that the measurement is projective. And here, when you post-select the data where the ancilla tells that the atom is projected in 54C, we see a nicely contrasted Rabi oscillation, which means that the measurement is projective. On the other hand, if we do not look at the measurement result, the state prepared by a pi/2 pulse is turned into a statistical mixture, and Rabi oscillation do not appear anymore. So we have all the feature of a genuine quantum non-demolition measurement of the circular atom set, which will be a very nice tool for the future. So before ending, I present here the last experiment where we also demonstrated the operation of exchange Hamiltonian now for circular states, which is really the tool for the last tool we need before going to the many-body physics. So basically, in the experiment, we prepare as initial state the 54 circular level together with the 53 circular level for a second circular atom placed like 20 micrometer, 30 to 20 micrometer with respect to each other, and each of this circular atom have a probe in the neighbor. And so it gives you an idea of the structure of the simulator we plan to build. Each circular atom will be associated with one or eventually several probes, which can be used at different times to measure this atom, that atom, or both at the same time. So here we measure them both at the same time, and we have already to play a trick in the probe in order to prepare this initial state. And the point is that a circular atom have only microwave transition. You cannot focus the microwave to excite this Rydberg atom to that, and that Rydberg atom to this other state. You find you need an optical way to control locally what occurs to the atom. And we use, first time, the probe for performing that. So when we circularize, we light shift both probes so that they are not promoted to the circular level. And when we perform a microwave transition, two-photon microwave transition from 52 to 54, we prevent the second atom to perform this transition by first promoting the second probe to the 45S level. So this 45S atom produces a dipole blockade on the microwave transition, and then after this step, we have prepared 54C, 52C. And then the interaction there, which is the same as the one we use for quantum non-demolition, can be also used for performing local addressing of circular atom state. And then the last point for inducing exchange between these two states is a single photon transition, a microwave pulse on the 52C to 53C transition. The first atom does not seize it because it's non-resonant. So everything is ready for observing exchange interaction. And in the experiment, indeed, we observe nicely contrasted exchange interaction for atoms separated by 30 micrometer from each other. And in this data, we have a post-selection process which allows us to keep the data only if both circular atoms are present, which gives this nicely contrasted exchange signal. And then we are very happy because now we did this again more carefully with longer time scale, and we enter a kind of new physics. So this kind of data, some of these were taken more or less during the school. Indeed, this is the exchange oscillation you observe when you have very strong bob, which prevents the atom to move with respect to each other. And you see that the coherence time we observe for this exchange interaction is already in the range of 60 microseconds, a time scale which was never explored by Rydberg atom quantum simulator. And interesting physics comes in when we look at the same evolution in weaker bottle beam trap. So we put less trapping of power, so the trapping is less strong. And we observe a collapse of this oscillation. So we were first unhappy because we observe only this part, and we say, okay, the system coherence is killed in a weaker trap because the distance between the atom fluctuates too much. Indeed, that's an effect which is not just related to fluctuation of the position of the atom, but it's already related to interplay between the spin state and the motional state of the atom. And the point is that when you consider the two eigenenergies of the exchange Hamiltonian, one is going up, the other is going down, which means that the two-body atomic states have one part of its wave function which feels repulsive interaction, and the other one is attractive. And when your two spins start to exchange, that will also spatially separate. And this collapse is related to the separation of this, which should reveal somehow some entanglement between the spin state and the motional state. And the nice thing is that if you wait for one full period of oscillation in the trap, the system is coherent. It's not just blurring by thermal fluctuation, and you have a nice revival. So we are presently doing a quantitative analysis of that. We have a model, and I think interesting feature related to spin motion couplings that which can be switched on and off depending on the power we put is an interesting feature of the system. So I think I'm running out of time. Here is the kind of general scheme of simulator we can build with a circular atom, chain of circular atom with here, in this case, pairs of ancillar atom, and then similar physics as the one which is already investigated, but we can focus on long timescale effects and observe propagation of excitation effect of this order. This needs to switch to cryogenic temperature, which is the next difficult experimental step that we have to achieve. So I will drop this where we are mentioning the other activities of the group around control of spontaneous emission, about using another kind of atom for using circular Rydberg atom for quantum simulations. Strontium atom is interesting because once you prepare one electron in a circular state, the core electron, which is an ion, have some optical transition, which gives another button to manipulate the circular state. So, and then I just conclude with more general consideration about where we are with the Rydberg atom quantum simulator and what are the technical challenge to address in order to go further. So the present performance is manipulation of hundreds, 200 typically atoms in the experiments. Now the trapping techniques develop very fast, and even if quantum simulation was not performed at that scale, now several experiments achieve control trapping of up to 2,000 atoms, 12,000 without, 6,000 without rearrangement, but it gives you the scale. So what will be the limit? So probably 100,000 is too much, and for a very technical reason, which is the available power you can have for building your tweezer, and with 1 milliwatt per trap. If you have 10,000 traps, you already need a 10-watt laser. So you can bat 30-watt laser for this kind of trapping, eventually 100-watt laser, but it will be difficult to have a kilowatt laser, especially because you will start to heat up the length of the objective that you use to focus the atom. But that's another story. You need very high vacuum, for which cryogenic environment is very favorable. You need to implement parallel rearrangement of the atom, which is the case in this recent experiment. And eventually, you can combine optical lattices and optical tweezers. That's a direction that is chosen in the group of Emmanuel Bloch. So I think that 10,000 atoms somehow will be within reach with present technology. More will be more challenging, but never say never. And here is the timeline proposed. I think this is proposed by Crera for the evolution. So they are optimistic because they mentioned more than 10,000 atoms in 2026, which is nearly tomorrow. And what kind of physics can be done to there? So here I have a resume of what was done up to now. The green line is known. Now the circular atoms are coming, and I guess that we can investigate new unexpected physics with this system. And thank you for attention. So I'm sorry I was a bit long, but maybe we can have a few minutes for questions.
So thank you, Michel. Questions?
Yes?
Yeah, thank you for the lecture, Professor.
Mm-hmm.
So to achieve the circular level,
Yeah.
you showed a radio frequency transition, and I would like to ask if it's a single transition or it's a kind of a ladder transition between levels that are equally spaced. Because
Okay, so here is the diagram. So the transition we perform along this line,
yeah.
and the spacing between all these levels is in the range of hundreds of megahertz. So in the field we operate, the frequency of all the transition is 250 megahertz. So all these transitions are degenerate from the circular to the elliptical level with m equal 2. For lower m, quantum defect I already introduced is perturbing the energy diagram, but all these levels are equidistant, and indeed that's a good thing because it means that single frequency is good for going here to here. That's a bad thing because also that's the same frequency if you go in the bad direction with sigma minus transition. So in the experiment we use two tricks to avoid that. We have a magnetic field making difference between sigma plus and sigma minus transition. And in addition, we use a sigma plus polarized radio frequency field. So that basically the probability to be lost somewhere here is very low. And we transfer the population from here to here by adiabatic transfer. We go across the radio frequency resonance by varying the electric field. And this is, in principle, very efficient. In practice also, in an atomic beam experiment in a cryogenic environment, we have like 99.9 efficiency for this adiabatic transfer. It's reduced in the present setup because it's room temperature, and during transfer, some atom decay. Okay?
Thank you.
Any other question? So, Michel, I have many, but can I ask one?
Yeah.
So you showed the results from Broadways and looking on preparing the antiferro magnetic state. And then you said it was very low probability of preparing this state.
Of preparing the ideal state.
Yeah, but
yeah.
No, continue. No, I was wondering, so they have to really post-select? So they have, like they do in each 100, they have two that are really antiferro and they throw away everything.
If the goal is to prepare the ideal antiferro, you can post-select, but indeed, as errors are dominated there by detection error, your post-selection is even... Okay, so, if you just post-select, you lead with only 2%. So indeed, this number can be improved so that the post-selection is very efficient. So the point is that many-body physics should somehow, at some point, be robust with the existence of a little bit of defects, because it's also the case in solid states. So it's clear that all the physics does not need preparation of the exact ideal state. So this number is here shown to show how good is the control of the system if you want to prepare the ideal state. If you tolerate from 1 to error, it's okay. Indeed, there is another cause of error or discrepancy between the phase diagram of the system in the thermodynamic limit. Some errors are some defects. I think it's not the worst. The side effect errors, it's not errors, but side effects are eventually important for 1 or 200 atoms samples. In 2 dimensions, it's not a catastrophe. If you go to 3 dimensions, you have a lot of border, and the boundary condition effects are limited. So I would say that boundary condition control is more a problem than the individual defect. Of course, if you want to do quantum computing, you don't want any defect. So this shows you how difficult this will be.
Final question. Yes.
Thank you for your talk. You mentioned that main problem with is the power of the lasers that you can reach, and the spatial light modulator is known to be not so efficient with light because it diffracts light, and more of the light is not used. Have you tried to use DMDs instead of spatial light modulators, and what problems
so
do you
we
have?
did not try it, and DMD are not very popular there because it's mirrors, but you have some space in between mirror. And I think that diffraction efficiency you get finally when you want to go to some angle is worse than SLM. So SLM, if you have a small angle, you have efficiency like 90, 80%. I think that DMD, so maybe you can correct if I am wrong, it's like 10% or? It can be half, okay. It can be half. So I think SLM with reasonable diffraction angle have more flexibility, especially the fact that DMD is kind of binary system for each pixel, whereas with the SLM, you can vary the phase so between discrete values, but the resolution is 8-bit or eventually 10 bits. So you have a more subtle control of the wavefront, which is important, I think, to have a good control of the size and position of the tweezers.
Okay, thank you.
Yeah. Any other very fast question? Otherwise, we okay. No. So thank you, Michel, again.
Thank you.
So, guys, I think we are going to take a picture of the conference because Teresa was not at the picture